Yes, in this video segment, I'd like to introduce to you the rigid connection icon that appears in the Connections tab of the 3D Experience Release 2022x. Uh, the, the native FEA solver for 3D Experience is the Abacus program, and some of these are well established in the Abacus CAE interface and tutorials, but uh, these segments are intended for people who want to use 3D Experience without having any knowledge of Abacus, or the Abacus users who would like to get into the 3D Experience, but they find the interface different and the icons different. So it's intended to target those people. They're very elementary videos. Okay, so here is the situation. First, description of the problem. This is the application, the action bar of the application that I'm talking about, the modeling, and there is the rigid connection and spring connection. I already have a video for spring connection, so we're going to concentrate on the rigid one. And there is the icon. There is some information on the online help, so I just leave it here in case you have to look at it later on at your leisure. We're going to do this for a problem that we know the analytical solution, and therefore we develop confidence that it can be done correctly uh, using the software. Now, here's the situation. We imagine that we have a structure like this. For example, these are the two ends, or have Young's modulus 30 e to the 6 psi. And this 2-inch piece in the middle is a lot stiffer than that, okay? That being the case, we know that this middle section doesn't deform very much, and therefore we can replace it. We can pretend that it's a rigid object, okay? The right end is clamped and the left end is subjected to axial force of 10,000 pounds. Okay. Now, based on elementary strength of material, we know that we don't have to worry about the stiffness of the middle section. It's infinite, but the stiffness of the two ends based on elementary strength of material is AE over L. And these two ends are two springs in series, and therefore the effective stiffness for the structure is going to be half of individual stiffnesses of these two, which are the same. So if you put in your numbers, you see that the effective stiffness, if you were to replace this thing with a spring, entire thing with a spring, then its stiffness would be 3.75 10 to the 6. And the deflection is going to be the force divided by the effective stiffness. And you put 10,000 here and effective stiffness, you're going to get 0.027 inches. So whatever we get, we're going to compare it with this number. Now, I'm going to do this thing the way it's described here, creating rigid, uh, basically connection between two end faces. Is done with the spider element that you can see here. I'm going to do it like this. It can also be done as four rigid, think about a rigid beam or rigid connection at the corners. But if you do it like this, the number that you're going to get is not going to match what we expect. In fact, this is going to be well, it's going to be softer than this structure up there, okay? So that's why the deflection here is going to be larger, and the stress of going to be is going to be different. Okay? Now, when we do the face-to-face, what I'm trying to do, there are three options as far as the coupling goes: kinematic, continuum distributing, and structural distributing. Now, these things, the origin of these go back to the rigid bar element RBE2 and RBE3 in the good old NASRAM program. I will have a separate video on the business of coupling type, and we're going to worry about later on. But I want to show you that there will be some differences. There won't be any differences between these two for this particular problem, where both pieces are basically solid elements, but for shells and beams and things like that, these will come into the picture. Okay, so just to show you for kinematic type, the deflection 20263 inches. Similar number here, continuum, and similar number for structural. So it really doesn't matter that much in this problem, okay? But if you look at the stress distribution, it will make a difference, okay? This is the kinematic type. There will be some garbagey things close to the two ends, but this is fairly uniform 10,000 psi as they're supposed to be, okay? These are identical. These are different. When it comes to displacement, they're all pretty much the same. Uh, I'm not going to do this thing for you, but if you actually go ahead and model it with four rigid connection at the corners, vertex to vertex, okay, you don't get those options, by the way, you can see that. And the numbers, deflection is going to be different, okay? And the stresses, of course, needless to say that in the blue area, they're all 10,000 psi, so no big deal. Now, if you model it with only one rigid connection, it will bomb out. Two rigid connection will bomb out. Three rigid connection will bomb out. It has to do with the fact that this is not a stable uh, structure. If you go back, for example, it can rotate in space. But anyway, let's go ahead and do this problem. So we go to 3D experience. Let's create the dimensions have already been changed. The units have been changed to imperial units. So let's go ahead and on this vertical plane, I will sketch a, a square which is 2 inches by 2 inches. Sorry, 1 inch by 1 inch. This is the cross section. 1 inch. Exit. Oops. Forgot. This didn't change the unit here. 1 inch. That's better. Exit. Padded by 4 inches. 4 inches. Okay. Now I'm going to create a plane offset from this by 2 inches. That's the middle section that's very stiff. And on that plane, I will sketch a square like that, 1 inch by 1 inch. But the easier way is to project actually that face, and then I get the rectangle that I want, the square that I want. Exit, and then pad it by 4 inches in the other direction. 4 inches. What did I do here? 4. Oh, let's see. Flip the arrow. Right. Let me see for a second. Yeah, 4 inch, 2 inch, 4 inch, I think. Yep, that's what it is. Okay, so let's apply a material to it. First of all, let's create it. Under tools, add the material. We'll call it steel rigid video. Okay, steel. Okay, this one now. Apply on this. And now we're going to make input the data, material values. So under structures, abacus multi-physics, mechanical, elasticity, elastic, 30 million psi, 30 with 6 zeros. and 0.3 Poisson ratio. Say okay. Good. Now we're going to go to structural model creation. Okay, how about standard? Okay, I think I decided on those values 0.394 coming from my slides, and this is 0.008, and the what is that? The selected geometry is that part, and we say okay. Good. If you want to see the mesh, just update. There we are. All right, so that takes care of this. We're done here. So yeah, we're going to go to, oh, wait a minute. No, we're still here. This is where we create our rigid connections. So under connections, there is the connections tab. See that? There's the connections tab. We already did the spring in the other video. Now I'm doing the rigid connection. Okay. For support 1, I use this face. For support 2, I use that face. Okay, notice that it puts this kind of thing that looks like a beam. It's got a rigid beam element. It puts it there. And that, see, they have different options: kinematic, continuum, distributing. So why don't I do one of these? I will do the, for example, continuum. But the continuum, I'm not going to do all 3 of them. All you have to do is to change the type of coupling and then run it, and of course you're going to end up with these situations. Okay, so we say fine. Now this is done. So now we're going to go to the structural scenario creation. We use the element that or finite element model that we use. Good. So now as far as the restraint goes, oh, first of all, as far as the procedure, we're going to do static analysis. Linear problem, although I will use the include geometric nonlinearity there, but it's a small displacement, so it's okay. And then we go to restraint. We're going to clamp this end, okay, and then we're going to apply a load of 10,000 psi here. So load force on that face, and in the direction x 10,000 psi, not psi, 10,000 pounds. The force was pound, not psi. Psi is pressure. Okay, that's pretty much it. So we go simulate. Let's check the model first. I don't anticipate any problems. Then simulation, in case there are any issues. Notice the spider elements are automatically created internally. Actually, you know what I'm going to do? I will do the kinematic. This is the this was the, can't remember. This was I think this was kinematic. I'm not sure, we're going to check that. But I will do the other one, for example, the continuum one, and put them side by side for you to look at. How about that? I already have a video segment on how to do things like this, where you do 2 runs of different things and put them side by side for comparison purposes. That's going to be a great idea for you. Okay, let me check to see, by the way, what this, well, let's run it. We can check it later. I think this was kinematic. I'm not sure. We'll find out. Okay, now it's running. There won't be any problem. There may be some warning messages that it's good idea to check all the time, but I'm sure it's going to be okay. This business of being able to put these two different runs side by side, it's a great tool that you should use it to your advantage. Okay, quick run. It finished. It's extracting the results. Just bear with me for a second. There we are. Okay, let's close this. Okay, so that is this guy. All right. And the displacement, well, actually, we can figure out what is 1.1 e to the 4 maximum stress. I think this looks close to that, so we'll find out. Okay, so how do we find this out? Go to the what is this? Go to the branch which says like engineering connection, expand it, double click on it, and see it says continuum. Sorry, this was continuum. Continuum. Okay, good. So let us change this. Let us change this to let's say kinematic. Okay, everything is the same. All we did was the nature of coupling type. You say okay. So go back to scenario and run it. When you try to run it, it's going to ask you a question, should I overwrite the previous result or not? If we say override, it completely gets rid of the other one. If we say no, keep it, then it's going to keep it so that we can put it side by side. See that? Override previous, keep previous, and you can put a name here, for example. The previous one, previous is going to continuum, right? It was a continuum type. Okay, so now it's going to run the new one, but keeps the old one uh, at your disposal. Yeah. I think this is a very useful, as I said, this is a very useful tool that you can use it a great deal to see how differences come about when you make some changes in the model or loading, etc. I'm not sure how many of them you can keep, but I have a strong feeling it's just two at a time. I'm pretty confident only two, but you may want to play around with it and see whether you can do three. I doubt it. Okay, good. So let's get rid of this. This was the kinematic time. Remember that bulges, these bad, weird stress distribution at the interface? That's fine. So now, so what we're going to do is we're going to go to, I think under tools, no, not tools, under perhaps display. Yeah, under display, the display tab right there, there's this thing says compare results. So what happens is that you get this window and notice that you have results from structural analysis, and then this is the previous one, right? So for example, uh, already we have the stress contour, already you have one meter stress contour from the current analysis. Let's say you want to take the displacement, drag it, just drag, and put it there. Okay, good. Now you go to the previous one and select whatever you want. So let me make this thing bigger. Okay, so you go to the previous one, take the one Mises, drag it and put it there. And you can split these windows into other windows too, but I'm not going to do that. And then the displacement of the previous run, and put it there, okay? And then when you're done, you say, okay, there we are. Now these are the different, these are the steps that we don't want. For example, let's go to this window. I don't want the first step, I want the final step right there, okay? So let's make sure these are all the same. Yeah, so this is from the final step of the, this was the previous one, right? Which I called kinematic, by the way. So you move these things around. Remove this, yeah, put it there. All right. So these are all the final results for the two cases. This is for the current case, which was the continuum. No, this was for, which is what the kinematic one, and this is from the previous one. See that previous one, displacement and the stress. And you can, by the way, save these screens, etc. But I don't want it, so I just close it and don't save, and we're good. Okay, that takes care of this video. Good luck.